All right, so today I'm going to be talking on the detection of increased dosimetric uncertainties in OSLD readouts using in-house quality control metrics developed by the ACDS. I have no conflicts of interests and I have nothing to disclose. All right, so in terms of the actual equipment used for the ACDS Level 1 audit, we started off by commissioning the InLight MicroStar reader system from Landauer Inc. So in this image, you see the cassette holder, which holds the actual OSLD, the reader itself, a scanner for scanning the barcodes, and the laptop, which has the MicroStar software. Then later in 2018, we commissioned the MicroStar 2 reader, so the successor to the original MicroStar, also from Landauer Inc. And what we see here is the reader, the drawer, which holds the OSLD, and a scanner for scanning the OSLDs. The major difference is that the readout successions are automated by the software for the MicroStar 2 reader, whereas for the MicroStar 1 reader, you have to physically turn the knob backwards and forwards to activate each successive readout. And of course, we have the InLight nanodot dosimeters themselves, which are also from Landauer Inc. So here we see the three different states of the dosimeter. Here we have the closed position. Here we have the sensitive element exposed, which is what the state would be during the readout. And this is a side-on view of the dosimeter. So the actual sensitive element is a 5mm diameter disc of aluminium oxide, which is 0.2 millimeters in thickness. And over here you can see some really nice micro CTs of the OSLD. So over the course of ACDS Level 1 auditing over the years, as you can imagine, we've accumulated quite a lot of data. So what you're seeing here are the Australia and New Zealand data sets for the photons, electrons, and electron R50 variation plots, with the variations on the y-axis and the nominal beam energies on the x-axis separated into separate series. And there's a lot of data there. So every dot you're seeing here is an individual audited beam that has been measured. So a total of 2,224 photons and 3,209 electron beams have been measured across Australia and New Zealand to date since 2011. And that works out to be greater than 17,200 LCDs being used for audits. And if you do the maths, it actually works out to greater than 84,000 individual LCD readouts having been performed to date. This is possibly the largest database of readout data available. So all of our LCDs are separated out into batches of approximately 170 apiece, and we have a total of 28 batches currently being used for audit operations. So part of the process of establishing a new batch is to establish what is known as the element correction factors. And we do this by delivering a uniform cobalt-60 dose to the entire batch of OSLDs. We then read out each individual OSLD over 4 consecutive readout sessions. And in doing so, we can also then use the readout statistics to commission new readers and to determine their initial uncertainties. So because we read out each batch 4 times, we end up with 4 measurements of the ECFs for each individual OSLD within a batch. So then we can use those statistics to assess the average reproducibility of each individual OSLD ECF across the 4 readout sessions. And in doing so, we then establish the reader standard uncertainty. And we do this again as part of reader and batch commissioning. So we can plot these reader standard uncertainties versus time, and we can separate out the different reader types into different series. So the various shades of red are the MicroStar 1 type readers which we've commissioned, and the different shades of blue are the MicroStar 2 readers which we've commissioned. And what we found when we first commissioned the MicroStar 2 reader that we had is that it had the best reader standard uncertainty statistics to date that we'd ever measured. And we can take the averages of the reader type. So for the MicroStar 1, we find an average standard uncertainty of 0.38%. And for the MicroStar Reader 2 type, we find an average standard uncertainty of 0.26%. So those reader uncertainties are all well and good for when we're commissioning our readers, but we use our readers throughout the year for many years to come. So of course we need an ongoing way of tracking the uncertainties and the reader performance. We actually do this indirectly via the standard auditing process. So when a batch is prepared for audit, we set aside 16 control OSLDs, which we deliver a known dose to via our LINAC. These control OSLDs are then read out simultaneously with the audit OSLDs over 2 readout sessions. And in doing so, we can calibrate the audit OSLD signals. And we now have 2 obvious metrics of tracking the reader QC in the standard deviation of the individual audit doses across the pair of dosimeters, and also the standard deviation across the measured control doses, which, as it turns out, is our primary metric of tracking reader uncertainty. So of course, as with before, we can plot the standard deviations across the control OSLDs versus time, and we end up with quite a nice timeline image, which tells quite a nice story. So again, I've separated out the series by color into the different reader types. We have the red series representing the MicroStar 1s, and the blue series representing the different readers of the MicroStar 2 type series. You can see here, in late 2018, we replaced the MicroStar 1s with the MicroStar 2s, and we never looked back. But then shortly after commissioning these MicroStar 2s, a couple months later, you can see this shoot upwards in the standard deviations, and we were left scratching our heads wondering what was going on. Well, it turned out that this was due to physical wear on the drawer, physically grinding the drawer down because of the high workloads that we put the readers through. So once we became aware of that, our QC improved, we rectified this, and we brought our readers back within spec a couple months later. And then in late 2019, we commissioned a new MicroStar 2 type reader. And of course, at this point, we're well versed in drawer wear. So we are on top of this for the foreseeable future. We keep our readers within spec. And then all of a sudden here in in early 2021, we discovered a new error, which was causing physically larger standard deviations in our control OSLDs, and it turned out we couldn't fix this ourselves. We had to send the reader back to the US for servicing, and the problem turned out to be the actual photomultiplier tube optical engine within the reader, which of course we can't fix. So they did their servicing on it, they sent it back, and in the meantime we were using our original MicroStar 2 that we bought. We received the MicroStar 2 back a couple months ago, and we've been using it ever since. And as you can see, post-service, everything is nice and tight and within spec. So I just really want to quickly show you all what I mean when I'm talking about physical drawer wear. This is what it looks like. So this is the OSLD reader, this is the drawer, and if you pull it out and flip it upside down, this is what we were left with. So you can see the physical grinding on the grooves of the drawer, where it's not only worn away the paint, but it's also stripping away bare metal. We open and close our drawers approximately 9,500 times a year, which is well beyond the regular workload to be expected of these readers. And therefore we have to be on top of this, and we therefore replace our drawers annually. And the important takeaway of all this is that our QC metric has successfully detected an increase in dosimetric uncertainties due to a gradual physical change of the reader state. So now we can start looking at how this reader uncertainty affects the audit uncertainty. So each point here on this purple graph represents the standard uncertainty between OSLD number 1 and 2 between the pair of OSLDs in the measurements. And exactly as you'd expect, there is a detectable observed increase in the audit measurement standard uncertainty during times of poor reader uncertainties, which again seems intuitive, but now it's nice to have the data to back that up and to show it there. So another metric that we can look at is the readout reproducibility, represented here on this green graph. So each point here represents the percentage dose difference between readout sessions 1 and 2 per OSLD. And what we see is during this time of increased reader uncertainty, it's not reflected in the dose differences between readouts. What we suspect is that the OSLDs are extremely positionally dependent, and the micron level grinding away of the drawer was causing a physical change into positioning of the OSLD in the reader, which produced a signal which was different to the expectation value. So this created a period of high noise in the reader. This was reproducible though, as demonstrated by the percentage dose differences. So if we flipped this the other way, and we can look at it this way. So if we were only looking at the absolute differences between the readouts and just only assess the readout reproducibility as our primary metric, we might not have picked up this period of increased dosimetric uncertainty. So therefore, we must conclude that there is very little observed effect on the dose percentage difference between readout sessions during this specific time of poor readout uncertainty. And finally, of course, we want to know how the reader uncertainties correlate with the noise observed in the audit results. And unsurprisingly, when the noise of the reader drops, the noise in the standard deviations of the audit results also follows. So therefore, we conclude that there is an observed detectable decrease in the standard deviation of audit results with the improvement of reader uncertainties. Okay, so in conclusion, we have analyzed multiple different QC metrics on OSL dosimetry for a number of years on several thousand data points, and we have brought data to support our answer to the question, which metrics detect and are affected by equipment failures? So the take-home message of this is that we all need to be careful about which quality control metrics we use, and we need to recognize that different metrics will ultimately show, or they can show, mutually exclusive things in the overall reader quality control. And a secondary conclusion, which wasn't the aim of this project, we have shown an improvement towards the last quarter in level 1 dosimetry. And this could either be due to the ACDS having improved our level 1 dosimetry through our careful reader quality control, thus tightening the overall audit result statistics, or Australian and New Zealand facilities have improved their dosimetry, or both. It's probably both. Thank you all for listening to my talk. I appreciate your attention.